Hello, welcome to a new tutorial presented by the Associativity TV. In this tutorial, we are going to see differentiation in mathematics. So, what's differentiation all about? Differentiation is a chapter in mathematics which is involved in the calculation of gradients when we are given a function. So, if you are given a function, let's say y equals to x squared, if you want to know the gradient of that function at any point, you need the chapter differentiation. So before we start this chapter differentiation, we will see a little bit an application here. So let's take your case. Let's say any person who is seeing any of the audience who is seeing the video, you are the one who is climbing a mountain. Let's say you climb a mountain, and then you turn around the mountain. Now, you realize that there are different degrees of steepness as you climb the mountain. At this portion of the mountain, it will be very difficult to climb that portion because the degree of steepness here is very high. At this portion, the degree of steepness is becoming low, and at this portion, the degree of steepness is flat. You realize that the steepness here is 0 because the plane is a plane surface from here, and then from here, the degree of steepness decreases. Now, if you want to calculate the degree of steepness at any point of the mountain, you need the chapter differentiation. So what do you need to do in order for you to know the degree of steepness at each point of the mountain? The first thing you need is the function of the mountain, that the function that the mountain covers. So this function resembles a quadratic equation with a which is less than 0. So you have this quadratic equation, then you require the chapter differentiation in order for you to find the degree of steepness at each point of the function of the mountain. So you see in the letter section how to differentiate. So let's start differentiation. Now, to start with differentiation, we are going to start with certain formulas that each of the audience must put in mind when they are solving it. Now, so we are required to have certain formulas before we start the chapter differentiation. So we are required to know all these formulas, to memorize these formulas in order for us to differentiate each of the functions that we're going to see in this tutorial. So the first equation 2.1 states that the differentiation of k is equals to 0 where k is an element of R. So the differentiation of any constant gives you 0. So that's the first thing you need to know. Differentiation is written as d all over dx, and the function is written in bracket, or it can always be written in the numerator as such here. So this is a function to be differentiated here, and this is a differentiation. How differentiation is represented as d all over dx. Another method of representing differentiation is by using f prime of x. So you can place f prime of x, and then it still represents the differentiation of the gradient function that you want to calculate. But it's preferable to use the dx all over the dy in order to start it. Now, so the first thing is dk all over dx. The differentiation of a constant gives 0. That's the first thing you need to know. And a simple proof for this is that if you climb a surface which has a constant steepness, you realize that the steepness is constant, is not changing. That's why the differentiation of that constant of a plane surface, let's say you have a plane surface, A plane surface has a stiffness which is 0. In this case, the decay of d of a constant is 0, because if you have a plane surface in front of you, you realize that the d or the stiffness of that plane surface is 0. This is simply the reason why decay all over dx gives you 0. Now, d all over dx of x raised to power n is equals to nx n minus 1. So you take the power n, you multiply times the constant here, and then you go and subtract the power by 1. So you have nx raised to power n minus 1. Now, d of sine x gives you cos x. Another thing to be memorized. The next one is d of cos x gives you negative sine x. And the last thing is d of tan x gives you sec square x. Now, proof for the above formulae. So it's not only necessary for us to memorize the formulae, because it can be forgotten at times in examination. So you can go with a quick proof in order for you to find it, but it's necessary for each of the audience to memorize all these basic formulas in differentiation. So now, how do you prove it? Before I start with the formulae which is involved in proving, I will go through a brief history of differentiation. Here we see the name Newton-Raphson method of differentiation, and this Newton-Raphson method of differentiation is a method which is used in order to the Newton-Raphson method is a method which is going to be used in order for us to prove these basic formulas above here. So now let's have a brief story on differentiation. At start of differentiation, Newton was having difficulties in mechanics. We all know that Newton is the father of classical mechanics. So upon the proving of the Newton's first law, second law, and third law, he realized that the definition of velocity states that the velocity is the rate of change of displacement with respect to time. Now, and he also realized that he defined acceleration as being the rate of change of velocity with respect to time. Now, when you see this rate of change of velocity and displacement with respect to time, you realize that they are going to involve d. This d above implies a d of a change of the numerator, and this d below show the d of the change of the denominator. So you realize that Newton has a very big difficulty in order for him to prove the rate of changes of displacement and velocity, in order for him to prove the velocity and acceleration formulas from a displacement function. So, as having this problem in order to calculate the velocity and acceleration when he was having some displacement function, he went to see the mathematician Raphson, and it was with the collaboration of Raphson that they created a method that was used to prove this formula above and to easily differentiate functions. So now let's see the method they use. So let's say we have this graph. In this graph, you realize that you have a curve here, x-axis, the y-axis. Let's say you have a point A on this graph and you have a point B on this graph. Now, in the previous example, let's say that this curve shows our mountain, and you, the audience, you are located at point A. Now, let's say you want to find the degree of steepness at point A. So the degree of steepness at point A is going to be the line which passes through the tangent at point A. So that line passes in this direction here. So this is going to be the line for point A. Now, the degree of steepness of the line which link point A and point B passes in this direction here. But you realize that the degree of steepness of point A, of that which passes directly on point A, and degree of steepness which passes through point A and point B, they are different. Now, realize something. If I shift slightly point B and I place point B toward point A, you realize that the degree of steepness of the line AB is going to slightly be closer to the degree of steepness of the line A. So this is what the Newton-Raphson method says. So you first realize here that the gradient, we know that the gradient is calculated, the gradient of the line AB is going to be calculated as the point, the y2 minus y1 all over x2 minus x1. Now the y2 is a y of b, the y of b is f of x plus the x, so I write it here, minus y of a is f of x. I all divide by x plus the x, which is the x of b, minus x. So this is the formula written here. So the gradient of MA is the change in y all over the change in x. This is equal to y of b minus y of a all over xb minus xa. Now you see all of them here. So it's going to give you all this formula here, and then this denominator is going to subtract to give you the x. Now, having the gradient of AB, of the line AB, you can now assume that if you shift B closer to A at every point, every time, you realize that the gradient of the line AB is going to be closer to the gradient of A, of the line A. So now, that assumption will be considered by using limits. Now you see that the distance from x, from the point x of b to the point x of a, is dx. So this is x plus the point x of b is x plus the x, and the point x of a is x. So this distance here is dx. So now if the distance which exists between them is closer to 0, so as the dx tends towards 0, you realize that you are going to have the gradient at point B. So you first have here the gradient of point of line AB is going to be given as this, and now to conclude that the gradient of point of line A, the gradient of line A is going to be the limit, since if you shift A of the point B closer to A, so it's going to be the limit as delta x tends towards 0 of this initial gradient. So we are going to use now this formula in order to prove now the formulae above here. So let's start. Proof for d all over dx of xn is equals to nxn minus 1. So let's say this. So let f of x equals to x to the power n. So when you have it, you have a first point a equals to x and y. So this is x and x to the power n, and the point b will be x plus delta x and x plus delta x always to the power n. So I just substituted x plus delta x in the function, that is f of x equals to x to the power n, to have the point b, the yb here. So now I'm going to calculate the gradient. The gradient of A is going to be this minus this all over delta x, and all this is going to give you this. So x plus delta x all raised to the power n minus x to the power n all divided by delta x. Now you realize that I'm going to do a binomial expansion of this. So when I do a binomial expansion of this, I have this, and all this. So this is the binomial expansion. In order to do the binomial expansion, I'll use the combination. I'll say the first element here is n combination 0 of x to the power n So the next one, delta x, will be seen raised to the power 0, as we're going to see in combination and permutation in next chapters. So plus n combination 1 x to the power n minus 1 delta x. So when you increment here by a power of 1, when you increment here by 1, you reduce the power of the first element by 1 and you increase the power of the second element by 1. So you have this, and yet when you increment by 2, you have n combination 2, you reduce the power of the first element by 2 and you reduce the power of you increase the power of the second element by 2. So this is how you do the combinations. And now to easily calculate combination, we are going to see it later. So now we are going to use now the assumption we said. So for the gradient of AB to tend toward the gradient of MA, it implies that delta x needs to tend towards 0. So you're going to say gradient of MA is going to be the limit as delta x tends towards 0 of this function above here, because this is similar to this. Now to solve this, to solve limits, so how do you calculate limits first? When you want to calculate limits, the first thing you need to do is to remove all the delta x as possible, which is found in the denominator. So I'm going to divide all through by delta x when I've done the expansion. So when you do the expansion, you realize that this x to the power n and this x to the power n are all going to cancel. So even if I've added it, they are going to be cancelled at first place. Now, how do you calculate the combination? This is n combination 1. In order for you to calculate combination, the thing to do is to go, when you want to do n combination 1, the normal formula for n combination 1 is n factorial all over n factorial all over n minus r all into factorial r factorial. So the formula for n combination r is equals to n factorial all over n minus r all into factorial n factorial. The formula was not written here because we are going to be treated in the chapter combination permutation as we're going to see later. Now, a simple method, another way of still visualizing this formula I've written above, is to decrement. When you decrement this and you remove the factorial, so this is n all over 1 factorial, you decrement one time and you put the 1 factorial under. So you write the power as you see here. Now the next thing you're going to do, if I decrement 2 times, so I write n and then I decrement by n minus 1, then I'm going to write 2 factorial here. Similarly, if I want to decrement 3 times, I'll write n into n minus 1 into n minus 2 all divided by 3 factorial. So that would be the next term. So all that will continue. I'm going to have this. So when I'm going to divide all through by delta x, I'll see that this will be all over delta x, this will be all over delta x, this will be all over delta x, and all that. So this element and this element are going to cancel. So we are going to have this lastly. So you realize that this delta x is going to cancel this delta x. Now, in order for you to solve the limit as delta x tends towards 0, we are going to substitute now 0. Initially we didn't substitute 0 underneath here because it's going to be impossible, and we don't want to have an impossible limit. So we first try to expatiate, and when we expatiate, now we divide it by 0. We put the different value of 0 inside. When we place a different value of 0 inside, we are going to have 0 here plus nx n minus 1, and all this here is going to have a term dx. So 0 is going to multiply all through, and here is going to have dx all raised to the power n minus 1. So 0 is going to multiply, and you're going to have the formula here, and this is proved. So your f prime of x to the power n is equals to d of x to the power n all over dx, which is equals to this, and we have proved your equation. Now the proof for the cos x. To prove the cos x, you see use a similar method, and now we are going to say now MAB is equals to sine into x plus delta x minus sine x all over delta x. Now, since you have this formula, I can use now the expansion series of sine x and cos x in order to prove this. You realize that the expansion series of sine x you are going to have the different terms of the expansion series of sine x are going to be distinguished by this formula. So you are going to substitute the first thing is going to be when n is equal to 0 here, and here for cos x, the first thing is going to when n is equal to 0. Yeah, now the next thing is when n equals to 1, the next thing is when n equals to 2, the next thing is when n equals to 3. So this is the expansion series of sine x, and this is the expansion series of cos x. Now we are going to substitute each of them now back in this formula. Yeah, you realize that we've initially proved this formula above here, and the proof for this formula states that the f prime of x raised to the power n is equal to n x raised to the power x raised to the power n minus 1. So we're going to use that first formula in order to prove this. So you have sine x and cos x here. Now you see that if we differentiate now the sine x, the d of sine x, you're going to place this outside. So if I differentiate this, I'm supposed to have this other one. So differentiation of this is going to give you this. So if you differentiate, this is a constant, this is a constant. When you differentiate it, I'm going to just subtract here by 1, and then I multiply by 2n. So you realize that you're going to have this similar. So this is the answer you're going to have if you differentiate this. So this, you realize that this is equal to this, and so you have proved your first equation here. Now to prove the next one, you still use the same method. You now differentiate this other formula, because you are now proving for d of all over dx of cos x equals to negative sine x. So I'm going to place I'm going to differentiate this second formula in order to prove that it's going to give you this formula. Now when I differentiate this formula, I have this, but realize that this formula is not similar to this formula. But if I do the expansion series from this formula and this formula, you realize that they are not going to be similar. So let's try to do the expansion series of this formula and you see. So the expansion series of this formula is when I substitute each of the terms of the formula by n value, which is element of integer. So if I say n equals to 0, when I place n equals to 0, I'm going to substitute all through n equals to 0 here. I'm going to have x. You can try it at home. If I substitute n equals to 1, you're going to have x cubed all over 3 factorial. If you substitute n, so this is the expansion series of sine x. The expansion series of sine x is given as x minus x raised to the power 3 all over 3 factorial plus x raised to the power 5 all over 5 factorial plus the formula of expansion series of sine x. Now the expansion series for the one that I've differentiated for cos x is going to be this. So the first term is when n is equal to 1. So when I substitute n equals to 1, I'm going to have the first term, and that first term is going to be negative x instead. Now the next term, n equals to 2, is plus x cubed all over 3 factorial. The next term, when n is equals to 3, is equals to negative x raised to the power 5 all over 5 factorial. So the expansion series that you are going to have with the differentiation of the cos x is going to be equal to negative x plus x cubed all over 3 factorial minus x raised to the power 5 all over 5 factorial plus all that, and the expansion series given to you. So now if you realize that this expansion series is similar to the sine expansion series that we had above here, just that it's a multiplication of x. So when I put x negative outside, you realize that this is similar to expansion series of sine x. This is why d of cos x with dx gives you negative sine x. Now so we have proved the major formula above there, but it's not required for you to prove, but only to know how to prove this major formula above. Now let's see the next section, some other formula to be noted. Some other formulae to be noted are the exponential functions. So you need to cram that, to memorize that the differentiation of an x of e of x is equals to e of x. So that should be memorized. And also the differentiation of ln x is equals to 1 over x. So these are the two proofs. These are two formulae that also need to be memorized. So how do you prove for the above formulae? So we prove this formula again by using the expansion series. We first know that the expansion need to know that the expansion series for e raised to power x equals to 1 plus x squared all over 2 factorial plus x cubed all over 3 factorial plus x to the power 4 all over 4 factorial plus you continue till infinity. Now, when you differentiate d of e raised to power x, you're going to have, when you differentiate 1, you're going to have 0. You differentiate this, you're going to have 1. You differentiate this, you're going to have this. You're going to differentiate this, you're going to have that. And when you're going to expand and solve all this, you're going to have this. This is similar to this function above. So it implies that the differentiation of exponential of x is equal to exponential of x. Now let's prove for the differentiation of the ln of x equals to 1 over x. So we first start by saying that let y equals to ln of x. Now from the law of the logarithms, when you have this, it implies that x is equal to exponential of y. So the d of x with respect to y. Now if I differentiate this with respect to y, I am going to have, you realize that I am going to have still e raised to power y, because we initially proved here that the differentiation of e raised to power x with respect to x gives you e raised to power x. Now if I differentiate this function now with respect to y of e of y, I'm still going to have e of y, and this is similarly what you have here. So this you are going to have e of y. Now the function here shows you dx all over dy equals to e of y. Now if I want to I will interchange the position and place x above here and place y below there and interchange series too. So I'm going to say dy over dx is equals to 1 all over e raised to power y. Now we know that e raised to power y was initially assumed to set to be x here, so it implies that dy over dx is equal to 1 all over x. So these are the different proofs for the formulae above here. So now we pass to the next section of differentiation, which states the techniques in differentiation. So our first point was to know the different the main formula involved in differentiation. Now when you have the main formula involved in differentiation, you need to know now the techniques in order to differentiate some complex functions. So when you're going to know these techniques by heart, you are going to differentiate all forms and sorts of function as you wish. Now let's start with the first technique. The first technique is the technique of associativity. So this technique states that if you have an addition of two functions, let's say f of x plus g of x, the differentiation of the additional function is a differentiation of the respective function which are added. So the differentiation of f of x plus g of x is equal to the differentiation of the first function f of x and plus the differentiation of the second function g of x, similarly written as this. Now if you have function of function, how do you do the differentiation of function of function? Let's say now you have f of g of x. Let's say that the function you have is f of g of x. So this function f of g of x, in order to differentiate it, it will be g prime of x times f prime. So it will be better understood by using the second formula. This first formula is difficult to understand, but by using the second formula you understand better. So it states that if you want to differentiate a function of a function, you will differentiate the internal function, which is g of x, with respect to x. you differentiate the internal function with respect to x, then you multiply times the differentiation of the external function with respect to the internal function. So this is what you need to know. When you have to differentiate the function, you differentiate the internal function with respect to x, multiply times the differentiation of external function with respect to the internal function. So you can do it at 3 levels. If you have one function which is above 2 functions, and you have the next function which is above the next one, you do it also at those 3 levels. So now, product of functions. So if you have multiplication of function, let's say I have f of x times g of x. In this case, what you do is going to be f of x times the differentiation of g of x. You do f of x times the differentiation of g of x plus g of x times the differentiation of f of x. So this is how to do with product of function. The technique for product of function is f of x times the differentiation of function plus g of x times the differentiation of function. Now the next one is division of function. So if you have a division of function, let's say you have f of x divided by g of x. The simple method to cram this division of function formula, you say d of bottom d top minus top d bottom all over bottom squared. So this is a simple method of cramming. Bottom d top minus top d bottom all over bottom squared. So this means that the d, when I say d, is differentiation. So it's the denominator, which is bottom, times d, the differentiation of the numerator, plus the differentiation of the numerator times differentiation of the numerator times the function of denominator all over the denominator squared. So you see it here. So you take the denominator of function, you multiply it times the differentiation of the function of the numerator, you subtract times the function of the numerator, you subtract the function of the numerator times the differentiation of the denominator, all divided by the function of the denominator squared. So this is different division of function. Now the next one is implicit function. If you have implicit function, an implicit function is just a function which is described as y equals to f of y. So an implicit function is written as such: y equals f of y. So you see that the main variable, which is on the left hand side, is still present itself in the right hand side of your equation. So normally you see that functions are with respect to another variable, let's say x or even z. So our function, you normally see that function are y equals to x squared, y equals to x squared plus 1. But now if you have a function y equals to x plus y or y equals to x plus y squared, those are implicit functions. So in order for you to differentiate that, you're going to use this formula, the d. In order for you to differentiate this, you're going to have dy all over dx is equals to, you differentiate the interior, we are going to use the formula of function of function. You differentiate the interior with respect now of dx. So you're going to have dy all over dx times, you differentiate now the exterior with respect to the function which was internal here, and the function which was internal here is y. So with respect to y, so you've used the formula for function of function in order to find for the differentiation of implicit function. And now, how do you apply the techniques above? So this is what we're going to see in this next section. Applying the techniques above in different examples. So the technique of associativity. So let's say let the y equals to 3x raised to the power 5 plus 2x squared plus 5. So now we know the formula is this. So our dy all over dx is the differentiation of the first one, differential of the second one, differential of the third one. The differential of the first one gives this, differential of the second one gives this, and the differential of the third one, which is a constant, gives 0. So your answer is this. Function of function. So let's say I have y is equals to sine of ln of 3x to the power 5 plus 2x squared plus 5. So this is my function. So you see that here I don't just have two functions, present inside, but I have three functions, a function of 3rd degree. So you realize that you have a function, let's say you have a function h, you have a function g, and you have a function f. So in order to do function of function here, the d of f of g of h all over the x here is equal to the differentiation of the innermost function. So it's going to be a differential innermost function with respect to x. So this innermost function, I differentiate it with respect to x, times I take now the middle function with respect now to the innermost function. So d of g all over the h, times I differentiate now the outermost function with respect to the middle function. So it's d of the function f all over d of g. So let's see how it works. So let h equals to 3x to the power 5 plus this. G equals to ln of h. So the first function is a ln, and is a ln of the innermost function, and we have f sine of the middle function. So you're going to have this is similar to this. So d of y all over dx is equals to, you differentiate the innermost function with respect to x, you differentiate now this function with respect to h, and differentiate this function with respect to g. Now you're going to have 15x to the power 5. When I differentiate it, I have 15x raised to the power 4 plus 4x. When I differentiate this with respect to dh, I'm going to have 1 all over h, and when I will differentiate this with respect to g, I'm going to have cos g. So you realize that h is equals to 3x raised to the power 5 plus 2x squared plus 5. I substitute here, I'm going to have this, and g is equals to ln of 3x raised to the power 5 plus 2x squared plus 5, and I'm substituting it here. So my final formula, my final answer will be this. But you realize that if you know this method, so I can easily write the answer of this without even doing any unnecessary effort. So when you're going to do it for a very long period of time, you're going to realize that you can do this function and solve it with very little effort. So try to practice to do other function, create function, and then practice with them. Product of function. So the formula for product of function is that you differentiate the first function, you differentiate the first function times you maintain the second function, plus you differentiate the second function times you maintain the first function. So this formula given, so you're going to have d of course x cubed times sine x cubed, and sine x cubed, I maintain this one, plus now I take this one, I differentiate d of sine x cubed times cos x cubed. So the answer, when doing all this you are going to have internally, you are going to have, this is a function of function. So in order to solve function of function, you know that the internal function here is x cubed. So to solve x cubed first, I'm going to have 3x squared all into the external function is sine. So I'm going to write negative sine x cubed here times sine x cubed, plus you see that in order to differentiate this, I know that the internal function is x cubed. To differentiate x cubed is 3x squared, and differentiate external function is cos of the internal function, cos of y, and y here is x cubed. So I just substitute, and when I write this, I expatiate and solve. I'm going to have the answer as such. Now, division of function. So the division of function will be used in order to prove the function that dy all over dx is sec squared x. Initially, one of the formulae that I told you to memorize was the d of tan x, or with respect to x, equals to sec squared x. Now, here we are going to prove for the formula of d of tan x equals to sec squared x. So we first start by letting y equals to tan x. When you let y equals to tan x, you know by trigonometry that we have seen in the last tutorial, that's tan x equals to sin x over cos x. Now we are going to use the formula for division in order to find this. So we are going to say the bottom, we take the function of the bottom g times the differential function of the numerator minus we take the function of the numerator times the differential function of the denominator all over the function of the denominator squared. So that's it here. So when you have this, you are going to substitute the different values. So you're going to have cos x here, because in the denominator you take differential of the numerator minus sin x differential of the denominator all over cos x bottom squared. So when you expatiate this, you're going to have cos squared x plus sin squared x all over cos squared x. But cos squared x plus sin squared x is noted as a peculiar function in trigonometry as being equals to 1. So 1 all over cos squared x is written as sec squared x. So the inverse of cos squared x is sec squared x, as we've seen in trigonometry in the last tutorial. Now let's see the last one, the application of the technique implicit function. So let's say now you have a function y is equals to x cubed plus xy plus y cubed. So this function here. So now to find the gradient function of this function, I'm going to differentiate this first part. So this is why we preferably use the dy all over dx notation, preferable more than the f prime notation. This is where it's going to be very useful. So when you differentiate implicitly, you say that this y here is a function on itself. So you consider y as being a function. So anything which is not x in implicit function is a function for itself. So this y here is going to be considered as function. So I'm going to differentiate y with respect to x is equals to, when I differentiate this x cubed with respect to x, so this is equals to this function here x with respect to x plus this other function here with respect to x plus this other function here with respect to x. Now so dy over dx equals to, when I differentiate it, I'm going to have 3x squared plus, now to differentiate this, I know that it's a multiplication of two functions. So x and y are going to be two distinct functions here. So now to multiplication of two functions, you're going to have, you know the method is you take the first one, you differentiate the next one, you take the first one times differentiate the next one, so x times dy over dx plus you take the second one times differentiation of first one, differential of first one gives you 1, so you're going to have this plus you take this. Now you know that this is going to be a function of function. Y cubed is not considered as s cubed here. Initially I had x cubed only calculated as 3x squared, but with y cubed I initially told you that y is not x. So when you are differentiating the function y, always attach the dy over dx to it. So you consider the function y cubed here as a function of y inside the cube. So this is how we consider it. So when you want to differentiate any component of the implicit function with y, always attach the y over dx to it. So I differentiate it as similarly as I differentiate for x here. So I'm going to have 3y cubed twice squared times, I attach now dy over dx. So when I have this, I'm going to have this. So I expatiate all this. When I expatiate all this, I can bring it on the other side. I'm going to have this. So I place dy over dx as a factor. So my final answer, when I've placed on the other side, I'm going to place dy over dx as factor. So the final answer is going to give you dy over dx equals to 3x squared plus y all over 1 minus x minus 3y squared. So these are all the different application of the techniques we've seen above. We've seen the application of associativity, we've seen the application of function of function, we've seen the application of product of function, we've seen the application of division of function, and for implicit functions. So now, from here, you already know how to calculate the basics. You know all the basics of differentiation. So now we'll go now to differentiation of other complex functions. So now the complex function, let's say you have now differentiation of y equals to e raised to power sine x. Now you see that e raised to power sine x is a function just as easy as we said. So now this function here, sine x here, is a function in itself. So in order to calculate this, I'm going to do the function, which is the innermost function, sine x here. I differentiate it times I differentiate the outermost function with respect to innermost function. So I'm going to have g equals to sine x, f equals to e raised to power g. I differentiate g with respect to x times I differentiate f now with respect to g. So I'm going to have the differentiation of sine x, which is cos x, times the differentiation of e raised to power g with respect to g. I'm going to have e raised to power g still. So the answer will be cos x times e raised to power sine x. So the answer is given here. Example 2. Find the derivative now of y equals to e raised to power x. So now from this function, I'm going to use implicit function in order to calculate this. So I'll first start by using the law of logarithm. So the law of logarithm says that if I place a lane here, I'm also going to place a lane here. So the lane of y equals to lane of e raised to power x. So the law of logarithm says that lane of e raised to power x is similar as x lane of a. So it implies that lane of y is equal to x lane of a, where a is an element of real numbers. Now, differentiating by implicit function method, I will now use the technique of implicit function in order to differentiate this. I know that this is a function of a function. So lane y and y here is a function. So I'll first start by differentiating the innermost function. When I differentiate innermost function here, it's going to give you dy over dx. And now when I differentiate the outermost function, it gives you y 1 over y. So you're going to have this is equals to, I differentiate this with respect to x. So when I differentiate this with respect to x, what I'm going to have, you see that lane a is an element of real numbers. So a here is an element of real numbers. It implies that lane a is also going to be an element of real numbers or a constant. So it's similar to differentiating 5x. So when I differentiate 5x, I'm going to have 5. So it's similar to say when I differentiate lane a x, I'm going to have lane a. So my answer is going to give you this. So when I say dy over dx, now I'm going to place dy over dx as a main factor on the left hand side. I'm going to have y lane a. So now what is y? Y is equal to a raised to power x. So it implies that dy over dx is a raised to power x lane a. So from here we can already prove, you have a proof that d of a raised to power x with respect to x is equal to ax lane a. Now the differentiation of parametric functions. Before we start by knowing what is a parametric function. So what's a parametric function? A parametric function is a function which is not similar to a Cartesian function. A Cartesian function is one which relates the y-axis with the x-axis. But with the parametric function, there exists another variable which is going to relate the y-axis with x-axis. Another variable is similar for the x and the y coordinate. So usually the variable is taken as t. So example, if I want to relate the let's say I have a circle in front of me, or let's say I have a cylinder in front of me. If I want to plot the area of a cylinder with respect to the volume of the cylinder, I can use a factor radius as a parameter, because you know that the area of a cylinder is given as the area of the cross-sectional area of a cylinder is given as pi radius squared, and now the volume of the cylinder is given as pi radius squared times h. So from here you see that the radius relate both the area and the volume. So you have the cross-sectional area pi radius squared, and you have the volume pi radius cubed, pi radius squared times h. You see that the radius relate both the area and the volume. So the radius can be used as the parameter. So now in this case, I want to relate x and y by a complex function, and now both of the complex functions have a parameter t. So now how do I differentiate now with respect to parameter? So I'll first start by saying that the differentiation model f prime of x given as dy over dx. So when I have this, it's similar to saying this is why it's good to use a format dy over dx than f prime of x. So this is another importance of using the format dy over dx rather than using f prime of x. So now using this, you see that dy over dx equals to dy all over dx times dt all over dt. So nothing is changed because the numerator and denominator can still be cancelled. So now I'll interchange the position and say that it will be dy all over dt times dt all over dx. So this is a formula here. So now dt over dx is similar to 1 all over dx over dt. So now the formula for dy over dx is dy, we differentiate the function of y with respect to t times differentiate the function times 1 all over differentiation of function of x all over dt. So now let's coming back to the example above. We see that the function y here with respect to t is 2t minus 1. So when we differentiate this with respect to t, we are going to have 2 as seen here. And now the next function for x is t squared minus 2, and when we differentiate it, we're going to have 2t. So the answer is going to be 2 times 1 all over 2t, so it is 1 all over t. Now differentiation of second degree of the parametric function, we need to know what the use of differentiation of second degree. So the representation first of differentiation of second degree is you differentiate the first function you differentiated. So if you want to differentiate a function you have differentiated, it's going to be d squared of y all over dx. So this is not x but d squared of y. Now the second derivative of parametric equation is given as you have d squared all over y, d squared y all over dx is equals to d all over dx of dy all over dx. So you have this. Now you see that if you say d all over dx, now dy over dx, we initially prove that it is dy all over dt times dt all over dx. Now you see that you can interchange now the position of dt in order for it to become as such here. So if I place here dy all over dx, I place it at this position, I'm going to have dt outside. So I'm going to have d all over dt here, dy all over dx here, times I'm going to have dt all over dx, but dt all over dx equals to 1 all over dx over dt. Now for the question above, now if you're asked to find the differentiation of second degree, so the d squared y all over dx of the function here, this function above here, so this initial form parametric function t squared minus 2 and 2t minus 1, we are going to say now it is the initial function we've differentiated was 1 over t. We are going to differentiate it again with respect to t. So when we differentiate 1 over t with respect to t, we are going to place t above. So this is t raised to the power -1. We multiply here the coefficient by -1, so we're going to give -1, and then we subtract the power by 1, so we're going to have -2. So the answer is going to give you -1 over t squared. Now you multiply it times 1 all over dx over dt. Dx over dt was found to be 2t, so the answer will give you this. Now the next part of our differentiation will be the differentiation of inverse trigonometric ratios. So differentiate. So let's see example. If you want to differentiate the inverse trigonometric ratio, sine inverse of x. So we first start by letting y equals to sine inverse of x. Now when we let y equals to sine inverse of x, say that sine y is equals to x. Now we are going to differentiate it implicitly. So when we differentiate it implicitly, we realize that this internal function, we say that this y is not similar to x. So when you see the differentiation of an implicit function, anytime you want to differentiate a function which contains y, we need to attach dy over dx to it. So we are going to differentiate internally, say dy over dx times differentiation of external is going to give you cos of y. So when you differentiate sine, you have cos and positive, and not negative in case of cos, differentiation of cos. When you differentiate x, you're going to have 1. So now the dy over dx is going to be 1 over cos x from here. Now from the formula in trigonometry, a good formula in trigonometry, we know that sine squared y plus cos squared y is equals to 1. But it implies that cos y is equals to 1 all over the square root of 1 minus sine squared y. Now you know that sine y is equals to x. So you see that this formula, when I substitute here, you see that cos y was equals to this. So this one error, you know that normally if I place it here, I'm going to have cos squared y is equals to 1 minus sine squared y when I do this. So my cos y normally gives you 1 minus sine, the square root of 1 minus sine squared y. So 1 all over cos y is going to give you 1 all over the square root of 1 minus sine squared y. Now you know that sine squared y and sine y is equals to x. When I substitute it back, I'm going to have this. So this formula is going to give you this. So it implies the d of the sine inverse, because y here was sine inverse of x. The d of the sine inverse of x is equals to 1 all over the square root of 1 minus x squared. So now how do you differentiate now y equals to cos inverse of x? So let's see. We first start by saying that the cos inverse of x by trigonometry states that it's similar to cos y cos x. So when we differentiate, you first start by differentiating implicitly. Differentiate internally, you're going to have dy over dx. Differentiate externally, you have negative sine y, in contrary to sine, which is positive cos x cos y. So when you differentiate this right hand side, you're going to have 1. So we are going to have dy over dx equals to negative 1 all over sine y. So now when you do this, you're going to have the similar formula that we had this, but instead for sine y. So 1 over sine y, this is an error. It's normally supposed to be 1 all over sine y equals to 1 all over the square root of 1 minus cos squared y. Now using this information, you are going to have this. So this case is negative, so the dy all over the x now is going to be equal to negative 1 all over the square root of 1 minus cos squared y. So you know that cos y is equal to x. When you substitute it, you're going to have this formula. So the d of the arc cos of x is equal to negative 1 all over the square root of 1 minus x squared. Now how do you differentiate the tan inverse of x? Similar model is used. So say that the tan y is equal to x. Now when you differentiate the externally, by implicitly, you're going to have dy times differentiation of tan with respect now to x. Differentiation of tan with respect this, we differentiate internally. Internally, you're going to have differentiation with respect to x, and externally is going to be the differentiation of the external function with respect to the internal function. So you're going to have sec squared y. So when you have this, you're going to have 1 all over sec squared being dy over dx. So now we are still going to use this formula in order to associate with this. So sine squared y plus cos squared y equals to 1. We see that from here sine squared y all over cos, if I divide all through by cos squared y, we are going to have sine squared y all over cos squared y plus cos squared y all over cos squared y. So these and these are going to cancel. So you are going to stop by having tan squared y plus 1 equals to sec squared y. So you see a relation now between the tan and the sec. And here you initially had the tan of y. So from here I can substitute. And when I substitute, I'm going to have dy is equals to 1 all over, this negative is not present. It's not present here because we initially not have a negative. It's an error. So you have 1 all over 1 plus tan squared y. So lastly, you're going to have dy all over dx equals to, you know that tan squared y is similar because tan y is x. So when you substitute, tan squared y is similar to x squared. So d of the tan inverse of x will be equals to 1 all over 1 plus x squared. Now let's see, we have already, so if you are at this point of the tutorial, it implies that you already know differentiation. Now let's see how to apply it. So let's go back again to the introduction of the tutorial that we had. So at the introduction, we said that if you are climbing a mountain, you realize that the steepness of the mountain usually changes as you are moving up the mountain. So now, how do you calculate the gradient at different points of your steepness? So now let's see the application to this differentiation. So now the first thing in the application of differentiation is to calculate the turning point of the curve. In our curve that we initially had above on the mountain, you realize that the mountain was ascending, and then at a certain point it was at the peak, and then it descend. You realize that at the peak of the mountain, you are not going to ascend nor descend, but it's as if you are moving in a straight line. So in a straight plane, it's as if you are moving in a straight plane, and when you see straight planes, there is steepness there is considered to be 0. That is why turning points of curve are said to have a steepness of 0. So the turning point, so first thing is to note the definition of turning point. So the turning points are any point of a curve which is neither increasing nor decreasing but having a steepness of dy over dx equals to 0. Now there can exist two types of turning points. You can have maximum turning point, or you can have a minimum turning point. Now several functions are going to ask you to find if a curve has a maximum turning point or it has a minimum turning point. Example, if I give you a curve for a mountain and I give you a curve for a downward plane, and I ask you to find which one has a peak and which one has a bottom peak. So how do you do it? So it's by using the principle of turning point. So in order for you to find if there is a maximum turning point, the first thing is to find if there is a turning point. And to find if there is a maximum turning point, the first thing to do is to find if there is a turning point. So to find if there is a turning point, you realize that you're going to use a formula dy all over dx. Now the next portion, if you have found that there is a turning point, then you can find if the turning point is maximum. So the question is, how do you find if a turning point is maximum? In order for you to find if a turning point is maximum, you then need to note the definition of a maximum turning point. Now a maximum turning point is a turning point which was initially is a turning point of a curve which was initially increasing and then decreases the direction. So it's a turning point which initially had a positive increase in direction and then a negative or a decrease in direction. So this is a maximum turning point. A maximum turning point is at the peak, so it implies that before the maximum turning point there existed an increase in steepness, while at the end there was a decrease. So we are going to let's take an example in this case. So find if y equals to negative x squared has a maximum turning point. So we first start by finding if it's a turning point. If to find if it's a maximum turning point, first start by finding if it's a turning point. So if it has a turning point, so first differentiate. When you differentiate the function, you have dy over dx equals to multiply the coefficient -1 by 2. We're going to have -2x. Now you say that at turning point dy over dx equals to 0. So you see that x equals to 0. So there exists a turning point at x equals to 0. So to find the coordinate of turning point, you just substitute x equals to 0 in the initial function. So the coordinate of turning point exists at x0, y0. So this is a turning point. The turning point exists at x0, y0, so 0, 0. Now, in order for you to find if this is a maximum turning point, you will find if it was increasing before the turning point and if it is decreasing after the turning point. So there also exists another turning point. I've only set the maximum turning point and minimum turning point in this tutorial, but there exists another turning point, which is a null turning point. A null turning point is a turning point which before that turning point it was increasing, and then after it is still, the steepness is still increasing, or the steepness is still positive. So realize that with a null turning point, before the turning point, the steepness is positive, and then after the turning point, the steepness is still positive. With the maximum turning point, before the turning point, the steepness is positive, and after the turning point, it's negative. With the minimum turning point, before the turning point, the steepness is negative, and after the turning point is positive. So you just take, in order for you to prove it, you are going to take a number which is below the x coordinate of the turning point. So we are going to take the turning point x coordinate is 0. So we're going to take negative 0.1, and we take above it 0.1. So you're going to find the dy over dx at negative 0.1. You see that it is positive. When you substitute in the value of the dy over dx here, when you substitute negative 0.1, you're going to have a positive value. So you see that the turning point was increasing before the steepness was increasing before the turning point. And now when you substitute the value above, you are going to have negative. So you see that it's decreasing after, and this fulfills the condition of maximum turning point. So it implies that the curve has a maximum turning point. Now another method to find if the curve has a maximum turning point is just by finding the d squared y over dx. If the d squared y over dx is less than, if the value of the square y over dx is less than 0, it implies that the turning point is maximum. So this is another simple method in order for you to find a turning point. But I like to use the complex method because it makes me to know the nature of my graph. So with this other simple method, if you don't want to have cumbersome notes, you can use it. You just say the d squared y over dx squared is less than 0. So you differentiate this function again, and then you find if, when you substitute the x coordinate inside the double differentiation of the function, you're going to find if it is less than 0 or greater than 0. If the squared y over dx squared is less than 0, then you are going to have a maximum turning point. So you are going to, let's see, when you differentiate the differentiation of the y, you differentiate negative 2x, you're going to have negative 2, and negative 2 now is less than 0. So in the turning point is maximum turning point. So let's see now minimum turning point. The minimum turning point refers to, in order to prove with minimum turning point, what's a minimum turning point? A minimum turning point is a turning point which causes the curve to change direction from negative to positive. So now, in order to prove for the minimum turning point, first you need to prove it's a turning point, and then you have to test if it's minimum or maximum. So now, how do you test for a turning point to be for a graph to have a turning point? First, let's say you have this graph y is equal to x squared now. So you're going to say dy over dx equals to 2x. You see that dy over dx equals to 2x. So now at turning point, you see that dy over dx equals to 0. So it's 2x equals to 0. It implies that x equals to 0. So our coordinate of turning point, I will substitute x equals to 0 in our function y equals to x squared. Now I'm going to have the coordinate dy over dx. I'm going to have the coordinate of 0, 0 at turning point. Now I'm going to take a value which is lower than the 0 coordinate of turning point, and take a value greater than the 0 coordinate of turning point, and then I'm going to find how they are going to increment or decrement at a different level. I see that before the turning point it is decrementing, so it's decreasing, the steepness is negative, and after the turning point, when I substitute the value in the function, the gradient function, I'm going to have a positive. I see that it is increasing, so this shows me that it's going to be a minimum turning point. Now lastly, a null turning point is one which causes the curve to change from positive to positive. So it implies that the steepness before the null turning point is going to be positive, and the steepness after the null turning point is going to still be positive. So if you find that the value here is positive and then the value again is positive, then it's a null turning point. Again, the null turning point is also capable of changing the graph from negative to negative. So if you have it changes the steepness before the turning point, the steepness is negative, and after the turning point, steepness is still negative, then it implies that it's going to be a null turning point. So if you have a negative 0.2 and negative 0.2, you complete that instead a null turning point. Now let's see here. Again, a simple method to prove for a minimum turning point, you just need to say that the d squared y over dx squared is if the d squared of dx squared is greater than 0. For the maximum turning point, you had to prove if d squared y over dx squared was less than 0. But for a minimum turning point, you have to prove if d squared y over dx squared is greater than 0. So when I differentiate this, I'm going to have differential of 2x give me 2. So 2 greater than 0 implies that the turning point is a minimum turning point. So now the next application I'm going to see is the tangent line of a curve. So now this is the true part which will involve when you want to find the steepness of, let's say I want to really find the steepness of a particular point on the graph. So to find that steepness, I'm going to find the tangent line at that particular point. So if I want to find the tangent line of our mountain that we had at the introduction, if I want to find the tangent line that we had at of the mountain that we had at the introduction. So let's come back to the introduction and see the mountain had. So this is the mountain we had. So we have this point here, point A, and we have this point here, point B. So the tangent line, a tangent line is a line which passes tangentially, or it passes only exactly on one point of the curve. So let's say this line is going to pass and touch only point A of the curve, and then it goes up. This line is line A. So now how do you find the equation of this line? So to find the equation of this line is what we're going to use we are going to see in the next application. But at first we need some basic knowledge on coordinate geometry. On coordinate geometry, we know that gradient is given as this gradient of MA is given as y. We are going to say that it's going to be, in order to find the equation of this line, it's going to be y minus y of A divided by x minus x of A. All this will be equal to the gradient of A. So the gradient of A can be calculated from the gradient function of the curve, and we know the coordinate of y, and we know the coordinate of xa and ya. So let's see an example to see how to find the equation of a tangent line. So let's start. So equation of tangent line to a curve. So we say that m is equal to y2 minus y1 all over x2 minus x1, but this y2 and x2 can be considered just y and x. So let's come with an example. So let's say that we want to find the equation of a tangent at the point 1, 1. So if I want to find the equation of the tangent, you know that if I want to find the equation of the tangent exactly at the point 1 on the curve, when you have point 1 here, I substitute 1, I'm still going to have 1. So the equation of the tangent at point 1, 1 is equal to, so let's find it. We first start by finding the differentiation of the function. When you differentiate the function here, we are going to have 2x. Now you see that the gradient at point x equals to 1, you're going to have 2. So the gradient of the line above the line 1, let's say line A, will be also already equals to 2. So we have the gradient in mind. So we are now going to use this formula. So gradient here is equals to y2 minus y1 all over x2 minus x1. Now y1 is the point that we want, the y point, the y coordinate of the point we are looking for. So we have the y coordinate of the point and we have the x coordinate of the point. So we have 2 is equals to y2 minus y all over x2 minus x1. So now when we put it, we're going to have this 2 into that is equals to y2 minus y1. It implies 2x minus 2 is equals to y2 minus y1. So the final answer is going to give you y2 is equals to 2x2 minus x1 minus 1. Now y2 is compared to be similar to y on the equation of a line, and x2 is compared to be similar to x on the equation of a line. So your final equation of the line will be equals to y equals to 2x minus 1. So from here we've seen all the basics involved in differentiation, and we've seen that in order for you to understand the best of differentiation, apart as from the introduction, is that you need to in order for you to understand the best of differentiation is that you need to know the goal of differentiation. After knowing the goal of differentiation, you need to memorize the main formula involved in differentiation. After memorizing the main formula, you can prove the formula or you can leave them. So after doing that, you need to note some other formulae to be noted, and after doing that, you need to know the techniques of differentiation. So there are different techniques of differentiation that you have to use. So after knowing the techniques of differentiation, you need to know how to apply the techniques in different examples, as you've seen here. After knowing the application of different techniques, you need to know again the differentiation of parametric function. After knowing the differentiation of parametric function, you need to know how to differentiate trigonometric differential. And lastly, you need to know how to apply differentiation in real life situation with turning points, and how to find the equation of a line, as you have seen here. So from here we've seen all the different parts of differentiation in mathematics. So please like the channel Science Video Maker and subscribe it and share to your friends. Subscribe and don't forget to subscribe to have new video and to be noted when other good and better videos will be created. Thanks for your kind attention.